Hi everyone, you are welcome to Easy Science channel, ILA Excel Physics, WPH11 January 2021, part 3 of the unit 1. Shall we start with the first question? Actually, it is not the first question, it is the question number 16. I have done part 1 and part 2, and this is part 3. So my part 3 start with question number 16. So let's begin. A steadily increasing tensile force was applied to a sample of a titanium alloy. The sample had an original length of 40 cm and diameter of 5.05 mm. State the suitable measuring instrument to measure the diameter of the sample. So actually, the diameter is given here to 2 decimals. That means 100th of millimeter. So that is, it should be micrometer screw gauge and not vernier caliper. Because vernier caliper, it is given to 10th, 1 decimal. Okay, so now they are giving a graph. I have told you previously, when you get the graph, you have to read the y-axis and x-axis. Here y-axis is stress and it is given in megapascal. It's better to write 10 to the power 6 for the conversion of mega, then for your easy calculation, and go to x-axis. It is given in decimal points, so you might confuse. Therefore, it is better to write the width of the square. What is the difference between 0.02 and 0.01? That is the difference. It is 0.01. So you marked it is in your paper. So it is easy for you to calculate. So now we'll move on to the question. Part 1. Determine the Young modulus of the sample. Young modulus equal to stress over strain. So you have to go and find what is stress, what is strain for this. So go to the graph and find the straight line part. So this is the straight line part obeying Young's modulus. So then see, it is stress going to be 600 and the strain going to be the half of the length. That is, we have to find 0.01 divided by 2 will give you 0.005. Very easy. So you can find, substitute stress 600 into 10 to the power 6, strain 0.005, then you get 1.2 into 10 to the power 11 Pascal. So Young modulus is going to be 1.2 10 to the power 11 Pascal. So second part, the sample broke at point B. Determine the force required to break the sample. So breaking stress sigma is equal to F over A. But they are asking force now. So you have to rearrange this formula, normal formula, to what they are asking. It is force equals stress into area. They are giving mark for the formula, what they are asking. So remember, don't go and write what you know. You have to write what they are asking you to write. What they are asking. So they are asking the force. So you have to rearrange your formula to force and then only you have to substitute. Remember that, because they are giving one mark for the formula you are stating. Okay, so now I want force. It is stress over area. So stress here is breaking point stress. Go to the graph and find the stress according to the breaking point B. So you slowly come over here. Then you will find this is 1300. Half going to be 1300. So 1 square less is going to be 1 is 20. So 1 square less is 1280. That is megapascal. So you have to multiply by 10 to the power 6 to get the pascal. So then area. They have given diameter. When they give diameter, it is just for to find area. So it is first you have to find R by dividing 2. It is given in millimeter. So you have to have centimeter. So you are further dividing by 1000. Then you are getting 2.525 into 10 to the power minus 3. So that into squared will give you area. So I have worked out for you. So 2 into 10 to the power minus 5 meter square. Then you are getting force as 2.56 into the power 4. So that is in Newton. They are giving 4 marks. So 4 marks is for finding area, the answer, writing this, writing the formula, and also what is breaking stress. So I have given you all 4 points for you to understand. Okay. Then we'll move on to the next part. Okay. The graph below shows a linear section of the stress strain graph. So they have given this is what I wrote. So show that the area under the graph represent the work done per unit volume in stretching the sample. So you have to show what is area under the graph. First find area under the graph. Half stress over strain. So that we have to show it is the work done per unit volume. What is unit volume? Volume is area into length. So you know area is half stress over strain. So when you work out area, half F over A into delta X over X. So you rearrange this. When you rearrange this, half is 0.5 F and delta X. What is F and delta X? It is equal to W. Okay. So A and X, A into X, A into length, it is going to be volume. So you have found. Okay. This is, you have found work done per volume. Work done per volume. It is the work done per volume in stretching the sample. So you have shown already. So E equals delta W over V. You know how we arrive this? So you start with what you know and you convert what they are asking for. Okay. Now go to fourth part. The area under any stress strain graph represent the work done per unit volume. See, they are giving the statement again. Estimate the amount of work required to break the titanium alloy sample. Now see, estimation. So now you have to, what is, to find the area underneath the graph, we have to count the squares. So all together, so how are you going to count? It is not a fixed one, it's a curved surface, curved area. So better to count the whole squares. So I will teach you easy way to get the area of a curve area. So now you go to mean squares and numbered all. Altogether you are getting 23. So what the rest of the squares you have to count. So now here half, quarter, half, again half. So this whole thing will give you 1. Okay. Then 24. Then again go to next one. Then another 2 will give another 1. So that is 25. Then another 2 will give another 1. Then 26. Now almost you have 26. What about the other part? Small. So you write somewhere 26, and I will advise you to count small squares and divide by 100. Why 100? 10 into 10 will give you 100 squares per big square. So you count small squares and divide by 100. Then you will end up with correct number of squares, or else you can calculate roughly like this small part, and some over these two will give you half, like that. But I will advise you to count the balance part in small squares and divide by 100. When you do that, you will get 32 and half squares. You try. Okay, so 32 and half squares. Each box area, you know, box area. So you go to here I have mentioned, okay, one box is 200 megapascal and 0.01 into 0.01. So you know one square area. Okay, so you write each box area 200 into 10 to the power 6 to turn into Pascal, and 0.01 is the square width. So 32 and a half squares will be, you are multiplying by 32 and a half. So volume is going to be extension into cross-sectional area. Extension they are given in centimeter. That is when you convert it to 0.4 meter. So area is going to be WD over V. So WD will be area into V. So you multiply this. So your work is going to be, work required is going to be work done 520 joules. Okay. Now move on to 17, question number. So a mass M is held in equilibrium by strings attached to two clamp stands. The force meter records the force F in the upper string. The force in the horizontal string is P. The angle made by the upper string to the horizontal is theta as shown. So they have mentioned here not to scale. In some papers it is given to scale. If it is given to scale, you have to take all the measurements by measuring by your ruler. They are not giving any value, but here it is not to scale, they have mentioned, therefore you have to calculate. So you will go and calculate. Okay, the force meter allows force to be measured by means of Hooke's law. The extension of the spring inside the force meter allows the stretching force to be read from a scale. When the force applied to stretch the spring is 15 Newton, the extension of the spring is 8 centimeter. Show that the stiffness of the spring is about 2 Newton per centimeter. Now remember, they are asking per centimeter. So you no need to go and convert this to meters. Remember, I always tell for you to answer what they are asking. Write what they are asking. So now we want the answer per centimeter. So what is F? It is K into delta X. K is your stiffness. You all know. So stiffness is F over delta X. What is F? It is 15 Newton. What is extension? It is going to be 8 centimeter. AC, you are getting 1.875 Newton per centimeter. So you have to, they are asking for whole number. So you work for additional 1. So that is 1, you have to round it for additional 1. So now see, you have to round it, it is 1.9 Newton per centimeter, almost about 2. B part, When M is equal to 0.55 kg, value of P is 8.5 N. Calculate the value of theta and the extension of the spring in the force meter. So I told you previously how to resolve F. So along theta it is F cos theta, the other way F sin theta. So you know it is 8.5 N and this is 55 G. So what they are asking is, they are asking the theta, but we don't know F. So but you have two equations for theta. Then how to simplify? So you divide the two equations because we want to get rid of F. So you write F sin theta is 0.55 G, name as A equation. Secondly, you go and write F cos theta equals 8.5, you name as B. When you divide equation A from equation B, you are left with sin theta over cos theta is 0.55 G over 8.5. What do you mean by sin theta over cos theta? That is tan theta. What is G? 9.81. So very easily you can find the tan theta. Then go to the calculator, take tan inverse of the value. Then you are getting theta as 32.4. But again they are asking extension of the spring. How to calculate that? I have done for you. So now see, you draw this triangle, vector triangle. Here 8.5, here 0.55 FR. So this is the vector triangle. Okay, 8.5 from there head to tail, right? From there you write 0.55 and this is F. F is your resultant force. Okay, you come along 8.5 and from there you come head to tail. Okay, 0.05, then this point and the previous point. This is your head, this is your tail. So you came here. So then you now see, this is the other way. So this is head, this is the tail. So it should be FR is in this direction. Okay, 8.5. Yeah. So you have to have resultant force is this way. Okay. You have to mark here this way. So for extension, we have to find FR. FR is 8.5 squared according to Pythagoras, and 0.55 squared. You get the total and you get the square root. You are getting 10.07 N. So FR is K delta X. So you know the extension. Extension is going to be 5.37. You are giving for extra point and it is 5.4 centimeter delta X. So that is how you got. But this vector diagram, it is like this. Your resultant force should be this way, right? You have to make it correct. Now going to number 18. A spherical polystyrene bead is immersed in oil. The bead has diameter 4 into 10 to the power minus 3 m. The bead is released and moves upwards through the oil at a constant velocity. A part, complete the free body force diagram below to show all the forces acting on the polystyrene bead. You know, that is, upthrust is up, weight is down, again drag force. So these are the two forces. Show that the upthrust the oil exerts on the bead is about this much, 3.1 into 10 to the power 4 N. Density of oil they have given, it is 930 kilogram per meter cube. So you know density equals M over V. So upthrust is actually W. So volume of the sphere, 4 over 3 pi r cube. So you can find R. If you know R, you can find the volume. Okay. So M is going to be now 930, okay, into 4 over 3. M is going to be rho into V. So M is 930 and V is this. So upthrust exerted by the oil on bead is equal force exerted by the bead on oil. You know that. So U equals W equals rho GV. So now see, you are calculating this. You are getting 3.06 10 to the power minus 4. To show we have to go for one more significant figure, because we have to show 3.1. So you have to go for one more significant figure. I am always telling, if they are asking one, you have to work for one more significant figure. So you are getting 3.06. That means almost 3.1. So your upthrust is about what they want. 3.1 10 to the power minus 4 Newton. Okay. Now see, Stokes' law shows how the viscous drag on a sphere is related to its viscosity through a fluid. Stokes' law is only valid if the bead is moving sufficiently slowly through the oil. State the reason for this condition. So now the flow must be laminar. It cannot be turbulent, so that there can't be any interference. Okay, the flow must be laminar to obey Stokes' law. You all know. Now go to part 2. For Stokes' law to be valid, the speed of the bead through the oil must be less than VR. So they are giving VR. So you can calculate their VR. Okay, and V, our V. So you have to show our V is greater than their VR. If our V is greater than their VR, Stokes' law cannot be applied. So you have to find VR of given VR and compare with our V. Now see, so VR, okay, VR given formula, okay, 10 into viscosity of oil, density of oil, diameter of the bead, you are getting 0.132 meter per second. What is normal V? The calculation. So now we know F is 6 pi meter NV. So it is this much. So V is going to be F 6 pi RA neta. So V is going to be this. So we are getting 0.16 not meter per second. But according to the formula, okay, we are getting 0.132. Obviously, it is V is greater than VR. That means Stokes' law cannot be applied. Okay. Okay. So, and that will be the end of the part 3 of the unit 1. I think all of you understand very well. Thank you very much. See you in next videos of IL physics. Until such time, study well. Have a nice day.